Welcome back. Let's do a current voltage with a capacitor. We're given a current source applied across a capacitor. So there's a voltage across this with this polarity and a current I, which is what the source is providing. This is a 5 microfarad capacitor. They also give you a 12 volt at t equals 0, so the initial voltage across this thing. You're given this waveform of current in amps as a function of time in microseconds. See, 5, 10, 15, 20, 25, 30, 35, 40, 10, 20, 30, 40, 2, 4, 6, 8, and minus 2. So this has an initial current of 0 amps. So the current supply here is, well, it's very fancy. You could think of it as a programmable device that can generate a current changing any way we want it. And it's been set up to generate this waveform right here. Okay, so it starts out at 0, goes up to 4 for 5 microseconds, and then goes down to minus 2 amps for this distance, and then it goes up to 6 for a little bit, and then down to 4, and then down to 0 again. And you're asked to find the V of t waveform. Okay, so I'm gonna sketch or get that ready to go here on the V of t waveform. So this is time in microseconds. I'm going to bring all of these intervals down. And let's see, so 5, 10, 15, 20, 25, 30. So this is the voltage in volts. All right, so we're going to really just use this formula that we have that relates voltage to current for a capacitor. Right, so given a current in a capacitor, which is this waveform right here, this formula will give us the voltage. And so voltage is given by 1 over the capacitance, integral from 0 to some time of I d tau, so the current I d tau, plus the initial voltage. And here we're given the initial voltage. And this problem just boils down to solving this integral here for every one of these intervals, so 5 times. So we'll start off with the first interval. Let's call this A, and this little segment we'll call B, and this one we'll call C, and this one we'll call D, and then E. So A is from 0 to 5 microseconds. So the voltage V is given by 1 over the capacitance, or 5 times 10 to the minus 6 farads, integrated from our starting time, 0 to t. So these limits of integration here will give you a function of time when you're done. You have a value at the bottom and then a variable at the top. So that's just kind of a calculus thing. So I d tau for this interval is 4. So it's 4 d tau. Plus the V0 for this interval. The initial voltage at this interval is, the initial voltage is down here. The initial voltage is 12 volts. That's given. I just didn't plot it. So here it is, 12 volts. This is the initial voltage. And we know that it's constant there because the current is 0 here, and I equals CV prime. So in order for this to be 0, this would have to be constant, right? Because the derivative of a constant is 0. Okay, so we know that this is a constant 12 volts, not just at 0, but before that, because we're given this waveform where I is 0 for, you know, a long time here. Okay, so the initial voltage is 12. So that's our integral that we need to solve. Now I'm going to skip a couple steps just for brevity and solve this, and what you end up with is 8 times 10 to the 5t plus 12. So that's our equation of a line that fits in this interval here. We have the starting value, and we know that it's a line. And if we just solve this for the value at 5 microseconds, we'd know where to draw that line to. So I'll squeeze that right in here. So V at 5, and this is microseconds. Plug that in here. So this is 5 microseconds. It'd be 5 times 10 to the minus 6. Plug that in there, and what you're going to get is 16 volts. So that's the value at the end of this period here. It's 16 volts. So our first segment goes up like that. Okay, and we just got to do that 5 more times. So B, the interval is 5 to 20 microseconds, this section in here. And our voltage is given by our formula here, where now we're integrating from 5 times 10 to the minus 6 to t of the I value in that segment is minus 2, so it's minus 2d tau, plus the initial voltage at the start of this segment, which is 16. Okay? Now, once again, skipping a bunch of steps just to not have a bunch of sprawl on the paper, this guy ends up being 12 times 10 to the 5th t minus 14, which is a line segment in here starting at 16 volts. We can solve this guy at the end of our interval, which is 20 microseconds. So plug in 20 times 10 to the minus 6 into this guy, and what you're going to get is 10 volts. So we know that it ends at 10 volts. So this is our line segment. And if you're wondering how that works out, it's because I wrote down the wrong thing right here. So this should actually be minus 4 times 10 to the 5t plus 18. And if you solve that at 20 microseconds, you get 10. Okay, sorry about that. Just going right along here. So V for the interval of C is 1 over 5 times 10 to the minus 6. Integral from here, we're going to start at 20 times 10 to the minus 6 and go to t of, and the current is 6 amps, so 60 tau plus the initial voltage 10 gives us this answer, 12 times 10 to the 5 t minus 14, the one that I wrote down by accident up in here. And then solving that guy at the end of the waveform, which is 25 microseconds, you end up with 16 volts. So it goes back up to 16, like that. A couple more line segments here. So the D interval, just keep on solving this same guy over and over again. 1 over 5 times 10 to the minus 6 farads, integral from, now we're integrating starting at 25 times 10 to the minus 6. We're doing the D line segment, which is 4 amps d tau to t, plus the initial voltage 16. This is 16 right here. Work that out, crunch crunch through this and do the integration part, plug in the limits of integration, all that. What you end up with is 8 times 10 to the 5th t minus 4. Solve that at the end of the interval, which is 35 microseconds, and you end up with 24 volts. So this guy goes up to, go over here, goes up to 24 volts. And the last integral for the last interval starts out at 35 times 10 to the minus 6 to t of 0 d tau plus the initial voltage of 24 volts, which ends up just being 24, and it stays that way. It's just constant 24. So it just cruises on this way, which you would expect because the current value is 0, and once again I equals C V prime, so a constant voltage will give us a value of 0. Going backwards, we're integrating down and then take the derivative back up to check, right? Okay, that's it. Just apply this integral and keep in mind that you need to plug in the initial voltage for the start of the interval. Okay? All right. See you next time. Bye.